This video that we're working on is for the application of dummy variables in our regression. My base regression that I'm using, just for simplicity, is the log transformation. So in this case, we've taken our sales data, we've taken a log of it, and we've run a simple regression of sales is equal to AX, or A plus BX. So I have just two variables, my coefficient for X and my intercept. What I want to do is add some dummy variables to it. And the first step of that is there's three different types of dummy variables that we're going to talk about. The first one is known as a point dummy variable. You start by looking at your data. In this case, we can see that there's a constant slope here, roughly a constant slope here. There's a change in slope here, and then we're back to kind of the same slope that we had here and here. And then on top of the change in slope, we have 2 points where we see significant drops in our sales data. So your objective, or one of the things you're going to do, if you have these in your sales data, you may not, is explain where they're coming from. I mean, pretty much everybody should have some sort of bump or drop during the 2007 recession. So we have a global recession here. This one, as I mentioned before, my company's UTX. I did some research on it, and between 1996 and 1997, there was a currency crisis in Asia. The value of much of their currency got cut in half, so that meant their purchasing power went down, and UTX is a global company and does a fair amount of business over there. Alright, so the first kind of dummy variable I want to introduce is, as I mentioned before, it's called a point dummy. And it's there to control for one-time events. So I'm applying it in this case for 1997 and for 2007. And what happens is that the error that's associated with this particular point away from the line just gets taken away. That's why you'll see that there's no forecast error on either of the point dummy estimates. So you use these point dummies for one-time events that are not going to be repeated or are completely unpredictable. So, if there was a sudden drop associated with, say, a major lawsuit that happened, or you're a pharmaceutical company, you've got all these pharmaceutical drugs out there, one of your drugs suddenly causes lots of problems, and you're going to have to pull it out of service. Kind of a one-time event. It's not really going to be predictable as you forecast sales going into the future. So the reason you're using these is to make your estimate a little bit better. So my control here is the regular log transformation. My standard error is 1.04. When I add my point dummies to it, I've reduced my standard error to 0.096. The dummy variables, again, W2 and W1, are just absorbing the error associated with these, with a one-time event. These are not one-time events, but with a one-time event. So something that you don't want to incorporate in your model. So another example would be you have sales data that's falling along this line. There's one odd point that's way up, and then we go back and start falling on the line. Excuse me. You don't want that one outlier point to screw up your estimate of beta and alpha, so you add a point dummy to that particular outlier. That controls for it. It brings it back to the line, and you get a better estimate of what your future sales are going to be. So that's the point dummy. We've created dummy 1, dummy 2. Our line estimate down here, as we'll use our line estimate function, we're going to highlight our sales, we're going to highlight our X's, comma, comma 1, and then that control shift enter in order to get our coefficients set up they're going to go intercept X, dummy 1, dummy 2. We incorporate those into our forecast numbers and then back to our standard errors. And we can see, again, this is my base. We're high here, we come down, we go up, we come down. When I look, this is the error plots. And what we want is just kind of randomly bouncing around that 0 line. When we get to dummy 1, we've actually smoothed it out a little bit. This is one of the dummy variables where we've dropped it down. Here's another W variable where we've kept it from bouncing. So we got really nice small errors associated with those, but we still have significant trends that are going on. Alright, so that's the point dummy concept. The second one is change in intercept. So one way to control for these areas of changes in currency, for example, currency crisis, or for global recessions, is to allow for different intercepts. So in this case, we have one line that would normally go up this direction. We have one line that goes like right through here. And then we have one line that basically has the intercept of the equation. So what we want to do is basically we're going to create 3 intercepts. The first intercept is the main one for the whole regression. The second intercept is going to be based on dummy 1, and the third intercept is going to be based on dummy 2. So we have basically 1, 2, 3 lines. So we have 3 intercepts and a constant slope, roughly speaking, between the 2 guys. How do you do that? Well, my event here occurred in 1997. So I'm going to create a dummy variable that starts in 1997. And once it occurs, I'm just going to go ahead and leave it as 1 through my model estimate. And what that's going to do is load up an intercept. Instead of having one point that's going to be corrected, it's going to attempt to create a new offset for these particular points. And then dummy 2 is going to start in 2007 when my sales drop happen. And then we're going to leave it as 1 as we go out. So that's going to create a second intercept. And of course the third intercept is just the primary intercept of the regression. So I've got my X, I've got my dummies set up here. There's zeros until I want the intercept to occur, be estimated, in other words when there's a shift. And then we have zeros again until the shift occurs, the big drop right here. So I'm going to throw in my associated ones. We can see here that my standard error decreased again. Again, for dummies 1, we're at 0.096. For dummies 2, we're at 0.005. When we look at my error box, my error plots, it's starting to go up and down, up and down, up and down, like we're looking for. Still got a little too much trend here, probably a little too much trend here, but this first part is being modeled fairly accurately, which is good. It's what we're looking for. Alright, so that is using changes of intercept. You're just going to have a single line of ones that are coming down here to control for shifts or allow for multiple intercepts in the regression. Now that's not going to correct this change of slope here. We can see that these set of lines are about the same slope as these set of lines, which is about the same slope as these set of lines. It's not going to be exact. This is statistics, not algebra. But here we see kind of a big increase or a change in slope. And again, this is starting in 2001 and it's kind of finishing in 2006. And what is causing this in researching UTX is that they do a fair amount of military business. So we had 2 wars going on, replenishing the military, increased their sales significantly, changed their sales mix actually. So they're selling more high-end military equipment that's bringing in more cash, which is changing the slope of their sales. And as we go after the recession, we start to kind of back out of some of the wars. Things calm down a fair amount, and the mix apparently is shifting back to what we were at before. All right. So what we want to do is include a change of slope here. To do the change of slope, what we need to do is interact a dummy variable, in this case it's dummy 3, with my x variable. And that allows us to have two separate slopes as we come into this particular area. So I create my dummy variable. The slope changes, I said, in 2001, and it goes through 2006. So I create ones here. Just type in 1, 1, 1, 1, 1, 1. And then everywhere else I'm going to want zeros. This is a forecast number. Everywhere else I'm going to want 0. And now to interact it, I need to interact the dummy with the x variable. So all I'm going to do is multiply x by the dummy. So whenever the dummy is at 0, x, the interaction term is going to be 0. Whenever the dummy is 1, the interaction term is just going to be equal to what x is. Okay? So that's where we have 8, 9, 10, 11, 12, 13 whenever we have a 1 in the dummy 3 column. And in order for line S to work correctly, we need to have all of my x variables in a box, which is why we have dummy 3 set off to one side. Alright, then again we just go to our line S, we highlight our y's, which is the log of sales, we highlight the x's, which is going to be the interaction variable and the x, draw it down, and do our Control-Shift-Enter to create all of our numbers here. And then we apply that to our forecast. So in this case we're going to have the intercept plus the coefficient of x times x plus the coefficient of dummy 1 times C4, which is dummy 1, the coefficient of dummy 2, which is F34 here, times the D4 plus the coefficient of my interaction term multiplied by E4, which is my actual interaction term. And we go ahead and drag that forecast down. So our standard error of the estimate is decreased again to 0.079. Our error terms have gotten a lot better in terms of being able to fit the data. What we're most interested in is being able to forecast the data. So how do we do that in the forecast? Well, remember, dummy 1 represents another currency crisis, dummy 2 represents a global recession, and dummy 3 represents the U.S. being in a significant war. And the interaction variable is saying that, well, if we're in a significant war for UTX, there's going to be a change in slope of sales. So I want to forecast in 2012. My generic forecast is just 10.77, so that's just a function of x. If I think there's going to be a currency crisis in 2012, I would enter a 1 on my forecast and enter. You'll notice that the estimate changed. So if I have a 0 here, I'm at 10.77, but if there's a currency crisis, I drop slightly. If I think that there's going to be a war in that period in time, then I would enter a 1 in dummy 3 column. That's going to turn on my interaction variable so that now it is 19. I have 19 and 19. So if there's a war, my sales forecast goes up from to 10.97. Again, if we are not having a war at that point, then I'm just at 10.7 in terms of the volume. And you know, I can assume that there's, for example, here I have a currency crisis, no global economic problems, and no war. Now I'm going to make the assumption that the currency crisis has gone away, but it created a global economic shutdown, and we ended up with a war because of it. So now I have my new forecast. And then my forecast for 2013, in terms of the way my model works, I can say that there's no currency crisis, there's no recession, and in fact, there is no war. I hit page down, sorry, which takes my estimate to 10.87. 5318DummiesReg. So this is a way to develop a model that allows you to forecast the sales under different conditional events. We've developed this nice model to go ahead and predict what is in fact going on in the future. Alright, in terms of your project, I need to see at least one dummy variable that's a change in intercept, and at least one interaction variable that's a function of a change in slope. Now, some of you may not have in your data a change in slope. So if that's the case, just do it for the last 5 years so you can see how it works. You're going to add dummies, you're going to add interaction variables only to the regression that you think is the one that's performing the best, whether it's the straight linear regression, a quadratic regression. You don't want to use a quadratic with GDP because of the forecasting problem associated with it, although you do need to incorporate it in your analysis, or the log normal. A little bit about the comparing the standard errors between, say, my linear estimate, which is at 4.8 billion, and I'm going to go over here to my lowest standard error, which is associated with 2 changes of intercept and an interaction variable to deal with the change of slope. Okay? So, little note on logs. If this is the number 1, 10, 100, 1,000, 10,000, 100,000. So this is basically 10 raised to the 0 power, 10 raised to the first power, 10 raised to the 10th power, etc. If I do a log base 10 of this, so it's equal to log, you pick the number, and then you tell it the base, which in this, just for this example, is base 10, you'll see that the log of these numbers is 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. Now, one of the things I wanted to highlight, and I didn't quite highlight it right in class, was even though on the log scale you're going from 4 to 5, in the sales scale you're going from 10,000 to 100,000. So, for example, if 3.5 is 0.5 away from 4, 4.5 is 0.5 away from 4, but 3.5 represents half the distance between 1,000 and 10,000. 4.5 represents half the distance between 1,000 and 100,000. So they're not directly equivalent. So what we want to look at is converting this standard error to make it comparable to some extent with the standard error of like my linear regression. What do? Well, we're going to pick a number. In this case, I'm going to pick 11.01. And even though this is a standard error of 0.079, it's 0.079 away from the estimated value. So my estimated value here is 11.01, my forecast value. So when I want to calculate, well, how many billions is that off, right? I'm actually only 0.04 off from the actual number, but in terms of my standard error, what would one standard deviation away from that be? So we would look at this using the exponential function. I'm going to go ahead and delete what I have here. So exp is saying we're going to take whatever number it's here, and it's e to that number, raised to that power. So the first number we're going to pick is my 11.01, and then I need to add to it my standard error. So that would be plus 1 standard deviation. So I'm add to it my standard error. And then we need to subtract from this number the raising it to an exponential value of just this number. So 0.079 away from the number 1 is maybe an actual value. If we go from plus 1.079, we might be just slightly above 10. But if we're 4.079, even though the difference is only 0.079, we may be 10,000 above 10,000 or 5,000 above. So this is going to give us an idea. of comparing the standard errors between our log regression and our linear regression without logging the data. So in this case, on the upper side, we're looking at about 5 billion. On the lower side, it's not going to be symmetric. So on the lower side, we're going to start off with EXP of my 11.01. And then we're going to subtract from that the exponential of 11.01. And now we're going to subtract away the standard error associated with it. So the range, the one standard deviation range in terms of actual sales dollars is 5 billion on the high side with this standard error and 4.6 billion on the low side for it, which is still fairly reasonable. But I may be able to generate a better standard error, a better forecast model. I'm actually using linear. My guess is that a quadratic equation for my data would probably ultimately fit a little better, allowing for some different intercepts associated with it, and kind of, again, sort of a change in slope here. And then if you're doing a change in slope and you're using a quadratic, the x represents a linear change in slope, so that's the line aspect of it. But if you're using a quadratic, then your change in slope should actually be on the quadratic variable. So it'll allow it to be kind of flatter out here and then kind of steepen as we go through here. And then the intercept changes should adjust somewhat for the shocks that are coming from the global events, the currency crisis and the global slowdown. So that's the basic concept of using dummies. I'm going to create another video where we're going to go over our confidence interval calculation. Thanks.